Today we're going to be talking about friction. So at this point, we've got a really strong grasp on the basics of mechanics. Force equals mass times acceleration. We've experienced, talking about it in 2 dimensions. We've got a really good idea of how Newton's laws work. But so far, we've had to pretend that friction doesn't exist, as if, it was something that we couldn't really deal with. But no more. Now we're finally going to tackle friction. We've got enough understanding about mechanics to be able to really work with friction, really have an understanding of how to use friction in our work. All right. So first off, let's get a sense of how friction works intuitively. So imagine you've got a plank of wood that you're pushing along at a constant speed. So, here's some floor, here's some plank of wood on that floor, and we're pushing it along at a constant speed. Now, first thing to notice is that in real life, we're used to the idea that if you want something to move and it's, experiencing friction like everything always is, you have to push on it if you want it to keep a constant speed. It's not just going to have that constant speed unless you push on it, because friction is going to sap the energy out of it. So for the first time, we're saying that we need a constant force to keep that constant speed. Up until now, if we'd had any force at all, we would have had an acceleration automatically, because we would have been talking about it being on a frictionless surface. It might have been a very small acceleration, but we always would have had some acceleration because we would have had some force, unless all the forces are canceling out. Now we're going to have all the forces cancel out because we're going to have friction canceling out the force we're putting in, so we can have a constant velocity. All right, with that out of the way, we've got this plank moving along at a constant speed because we're putting some force into it. Now, which would be easier to push? Which would take less push? Which would take less force from us pushing on the plank? If the plank was on a floor that was made of wood, or if the plank was on a floor that was made of rubber, which one of these will stick together more? Which one will have more friction? Just like you'd expect. The wood is going to stick less and the rubber is going to stick more. If we want to make it easier on ourselves, we're going to want that wood floor. What if we were to put the plank on a sheet of ice? What will that do to it? It's going to make it even easier. Different pairs of materials have different connections. They behave differently with one another because of material science and chemistry and stuff that we're not going to really get into talking about. But friction is a pretty complicated idea and can be explored in lots of further courses, and there's lots of cool, interesting things to learn about it. But in our case, we just know that if you have different materials, you're going to have different frictions. Okay, different pairs of materials. That's an important thing to keep in mind. It's not just one material, it's the pair of it. If we'd had a rubber plank on top of that rubber floor, we would have had experienced even more friction. If we'd had an ice plank on top of that ice floor, it would have been the least of all. It's the pair together that gives us the friction between them. All right, let's talk about another thing for our intuition to deal with. Imagine that same plank of wood. It's on a wood floor, but this time we're going to put some sack of sand on top of it. So we've got some sack, right, on top of it, and there's going to be some amount of sand. It's going to either have 10 kilograms of sand or it's going to have 20 kilograms of sand. Which one's going to be easier to push along, the 10 kilogram sack or the 20 kilogram sack? Which one's going to have more friction reacting with that, more friction force for us to have to overcome? The 10 kilogram sack push on the plank or the 20 kilogram sack push on the plank? Which one would you expect? It's just like you expect. It's the 10 kilogram sack. More pressure means more friction. The harder we push on something, the more friction we're going to have to overcome. The lighter something is, the less friction it's going to have to overcome. Right. Assuming the same object and the same material for the incline, which of the following 3 situations will be easiest to push? This is similar to the pressure idea. Now we're going to start talking about the normal force. Which one of these would be the easiest to push? In all of them, gravity is pointing straight down. But which one of them would be easier? Which one would you expect to? Just like you'd expect, the steepest incline. Why is that? Well, we can explore that idea by looking at 2 extreme scenarios. The exact same object and the exact same surface, but very different orientations. One of them is a horizontal orientation, the other one's a vertical orientation. Which one of these is going to have more friction going this way? So here's our friction force, here's our friction force. Which one is going to experience more? The one that's sitting on it. Why is that? That's because this one has mg down here, and so it's got the pressure is the normal force. It's got force normal pushing that amount. How much does this one on the right? How much is the force normal? So we've got mg down here, but we have, there's nothing this way, So our normal force is going to be Fn equals 0. There's no pressure, there's no interaction, there's nothing holding it against the wall to cause friction to happen. If you push really hard on something, it's going to have more friction. If you don't have any push between the things at all, there's no way for the materials to interact, there's no friction between them. So if we have no normal force, we have no friction. If we have a lot of normal force, if we push really hard on it, we're going to have more friction. If we were to instead come along and push crazy hard on this, then we're going to have a resultant normal force that's equal and opposite. And we're going to have this normal force, because it's not going to blow through that wall. We're assuming that the wall is able to withstand that much force. We might actually be able to arrest the power of gravity, arrest the acceleration due to gravity. The force due to gravity will be canceled out, because we'll be able to make a really large friction by pushing really hard. And you can test this out in a real quick demonstration for yourself. If you take just a normal book and you go up to a flat wall and you just put the book up against the wall and then take your hand away, of course, the book falls to the ground just like you'd expect. And probably shouldn't do that, because you don't want to hurt your book. But if you were to put the book up against the wall and then push really hard with the flat of your hand, not under it, because then you'd be holding it up, so it wouldn't be friction, it'd be just direct force applied through your fingertips. But instead, if you were to push really, really hard against it, you'll be able to keep it in place, because you put so much pressure on it that the friction of the book against the wall is going to be able to overcome the pull of gravity. It's going to beat out gravity, and it's just going to stay still. So, just like you'd expect from all of this talking, friction isn't just weight. It's about how hard the object is pushed. It's about the pressure between the object and the surface, the two materials, the interaction. It's the normal force. And for those of you having trouble with calculating normal forces on inclines, which will come up later in our examples, if you're having any difficulty with that, I'd recommend you refer to the Newton's second law in multiple dimensions lecture, which is a few lectures back. It'll give a great explanation of how to understand how normal force comes up when you've got some angle theta in your incline. You need to be able to figure out, you need to calculate just how much of the gravity is perpendicular and how much of the force of gravity is parallel to the surface, because that'll really come up later. And so refer to that if it's giving you any trouble, because that'll be useful in a lot of our later stuff and in this lecture specifically. All right, to sum up, friction is based on the interaction between the two materials involved in it and the normal force of the object on the surface. What kind of materials we have, how hard the pressure is. The two things, the normal force. If we want to turn that into an equation, that's going to become the friction is equal to mu, and mu is going to characterize, mu is a new letter that we're introducing. It's a Greek letter. We're taking more letters from the Greeks, as we love to do. Mu is a Greek letter. It's pronounced like a kitten's mew. Mu. It means the coefficient of friction between two materials, and it's spelled, in case you're curious, it's spelled mu, but it's pronounced mu. It means the coefficient of friction between the two materials. It's going to change depending on what the materials are, and it's going to vary a lot depending on specifics, and we have to determine it experimentally. There's no easy formula for determining what it's going to be. You just actually have to go into a lab and get it, or look it up in a table. But even looking it up in a table is going to vary, because depending on the specific condition of your object, if it's dirty, if it's clean, if it's wet, if it has grease on it, if there's a layer of air, if it's operating in a vacuum, what things are happening between it, it's going to vary a lot. So it's basically up to you to figure it out in a lab, or to be able to look it up in a table where it's very, very similar situations to the way you're doing it, or it's given to you precisely in the problem statement. So figuring out mu can be a little difficult, but normally that's what our problems will be about, or it will be given to us in the problem. So once again, going back to the equation, friction's equal to mu, the coefficient that represents the interaction between the two materials, times the force of the normal force, the normal force, Fn. So mu times Fn. One thing to keep in mind that isn't explained is we don't have to worry about the area touching. It's not about the area touching. So if we had a block of mass m, and we had a table of mass m, but the same material on the bottom. So same material here, and same material here, same surfaces. It's not about the cross-section of the area touching the ground. It's just about the pressure. Why is that? Well, that has to do with the way friction works. It's what's happening on a really microscopic thing, because it's going to change it to, if we have a lot of area, the pressure per square area, the force per square area force per area is going to wind up being much smaller in the case when we've got that large surface. So same pressure, but it's going to be extended over a large area. Whereas in the table example, where we've got just those little feet contacting, it's going to be the same pressure, but it's going to be over a small area. So the total effect is going to be the same. Either a small force per area, but over a large area, or a high force per area, but over a small area, the total effect of the pressure is going to be the same. So you don't have to worry about the cross-section, you just have to worry about the interaction between the materials. All right, now one last thing, friction's a force. We know forces come as vectors, so what direction does friction come in? It's not going to go in the direction of the normal force. That's why our equation in the previous page wasn't with vectors, because it's up to us to figure out what direction friction is going to go in. Friction always opposes the movement. Whatever direction the thing's moving in, and keep in mind that's the velocity, not the acceleration. So whatever direction it's currently moving in is the direction that friction's going to point. Well, it's going to point the opposite way. So friction always is fighting current motion. So the velocity, whatever the velocity is, whatever that direction is, the opposite of that direction is the direction that our friction is going to move in. All right, so at this point, we've got a pretty good understanding of how force works. We've got this interaction between mu and the normal force. So let's consider these two diagrams here. We've got this block is going to be the same in both of our diagrams, and the surface it's resting on is going to be the same in both of the diagrams. So let's assume that F1 and F2 are both big enough to move the block, but also that F1 and F2 are equal to one another in terms of the magnitude. They're the same number of newtons. We don't know what they are, but we don't really have to care about that right now because we're just thinking in a general case. So, if F1 and F2 have different orientations but the same magnitude, which block will accelerate faster? So, if we break down our forces, the first thing we're going to do is break our force into components. And we can always do that because force is a vector. So we look at the vertical amount in force 1 and the horizontal amount in force 1. And over here we look in the vertical amount of force 2 and the horizontal amount in force 2. Okay. So we see what's going to actually do the thing that's going to actually do the motion here is this right here. It's going to be the actual horizontal motion is going to stem from the horizontal component of our force. So if we're instead looking at what the normal force is now, we need to figure out what's the normal force going to be. Well, in both these cases, we've still got gravity to contend with. We haven't dealt with gravity. So there's the force of gravity. And over here, it's going to be the exact same force of gravity. So force of gravity on both of them. Well, how much does the normal force have to be to cancel these things out? Before, we didn't have, before when we talked about force of gravity and the normal force, they were going to be equal to one another because the only thing, well, not always equal if we are on an incline, but if it's horizontal, they're going to be equal because the only thing creating the normal force is gravity, right? But in this case, if you push on an object and that object doesn't blow through the table, then that means that the table has to resist both the object's force of gravity, because it's already resisting that, and then in addition, the force that you put into the object. So the table, the surface, is going to have to resist both the force that's been put into it by ourselves, by the problem, and the force that's put into it by gravity. So on the case on the left, in the first case, it's going to have to fight both gravity and the amount of the force. So the normal force is going to be Fn over here. Well, what about over here? Well, in this case, we've already got this component over here is going to cancel out this component over here. So the normal force over here is just going to be this little smidgen down here, right? So in F2's case, we lift out some of the effective weight. Some of the effective weight, what the normal force has to be, is much smaller. So which one of these is going to have a higher friction? Well, this one's going to have a much smaller friction because it's going to have, and we should do this in red since everything else horizontal is red, it's going to have a much smaller friction because it's got a much smaller normal force. But over here, we've got this huge normal force in comparison, so we've got this giant friction. We've got the same equal force horizontally, so we know that the giant friction is going to wind up sapping more of the acceleration, and so F2 is the more efficient way. It's going to be the easier way. It's going to cause more acceleration. F2 will accelerate the block faster because it will have the smaller Fn. So it's really important to pay attention to the interaction between the force of gravity, but then also the forces that we're putting into our object. All right, one more thing to talk about is the idea of an object being still at rest on its surface and an object moving along its surface. So which one of these will take more effort, more force from us? To start a refrigerator moving, sliding on a floor, to start that refrigerator up, or keeping an already sliding refrigerator going? If we want to just start it moving up, in addition to creating motion requiring some amount of force from us to get that started, there's actually going to be this little thing of it. If we have to sort of like unstick it, we have to pop it off of where it's already located. It might seem like a trick question, but it really isn't. It really can take more force to start something moving than to just fight kinetic friction. Kinetic friction is going to be different from static friction. The friction of when it's moving is going to be different from the friction of when it's still. Why does this happen? Well, that's actually a really complicated thing to get into. We don't quite have the time, or this isn't really the place. It's something for future classes on chemistry and more physics and a real understanding. And friction is actually something that they're still doing lots of research into. So it's really complicated for right now, but it's definitely something that's interesting and understandable. But we don't really have the time to talk about it right now. But the exact reasons, a little too complicated, but suffice it to say that on a microscopic level, the two surfaces interact differently between one another. They're going to wind up interacting in a different way when they're still, and they're going to still than when they're already moving against one another. There's slight differences happening microscopically, and sometimes major differences, as we'll see in some of the numbers that we're going to see soon. All right, so static versus kinetic. If we're gonna be able to talk about two different kinds of friction, kinetic, the moving kind, and static, the still kind, the at-rest kind, we're gonna have to use a different coefficient for each one. So mu is now gonna split into two different categories. Static is gonna be mu subscript s, mu sub s, mu s. Kinetic is gonna become mu k, mu sub k, mu k. So we've got mu static and mu kinetic. All right. So one thing to keep in mind, in almost all cases, mu s is going to be greater than mu k. There are a very few special cases where this isn't going to be true, but as far as we're going to deal with in our course, it is almost always true. Sometimes they'll be equal, and there's really, really freaky materials out there where things get weird, and you can have mu kinetic larger, but that is definitely beyond the purview of this course. It's not something we're going to have to worry about for now. But if you got really interested in materials science, it might be the sort of thing you have to deal with in graduate school, but probably not something you're going to have to worry about right now in high school physics. All right, so applying kinetic friction is pretty easy. If we just want to have friction on an object, it's just going to be mu k times Fn until the object stops moving, and it's going to go in the direction opposing its current motion. Real easy. It's just a force that's just constant, mu k times Fn. What about static friction? Well, that's a little bit different. If we have an object sitting still and we push on that object, say, we've got some object like this, and it's giant object, and a guy comes up and he pushes on it lightly. It's going to be able to defeat him, but it's not going to go back with all of the friction. Like, if he were to push this lightly, if it's going to be able to cancel out this lightly and this lightly, and say it's able to cancel up all the way up to this big, it's not going to react with a static friction force in the opposite direction of this big every time. It's going to cancel out whatever is put into it. Static friction is going to cancel out up to the amount of force, up to its maximum amount. So the maximum static friction. Static friction resists an object starting to move it until it gets surpassed. So until we get to that really extreme case, we're always going to have the case that static friction is going to just oppose however much force is put into it. It's not going to put in more than that. It's just going to oppose the amount put into it until we suddenly get to the point where we're able to equal and then surpass static. Just that equal point is the razor's edge of flipping over into kinetic friction, at which point the object lurches forward, unsticks, starts to move, and then kinetic friction comes into play, and almost always mu k will be less than mu static, so we'll have some slight acceleration if we kept up a constant force. So static friction cancels out the force that would cause acceleration, but it never exceeds them. So that gives us this idea right here. The maximum static friction is equal to mu s times Fn. But keep in mind, that's the maximum static friction, not more than that, but just the maximum. It's the top amount that it can be. We're not going to see that every time we put any small force into it. It's going to be that's only the top amount that gets put in, and that's going to be mu s times Fn. All right, so what are some basic examples of mu s and mu k? So these are some approximate coefficients for friction, this table here. Keep in mind, these can vary depending on the specific situation and the condition of the materials involved. Like I said, if it's wet, if it's greasy, if there's air between the objects, if there's a perfect vacuum that they're operating in, there's certain material properties that can happen. For the most part, these are going to remain the same, but it's about the whole system interacting together. So it's really something that has to be experimentally determined or given to us in the problem statement, or something that we're solving for from the problem statement. So take a look at these, and this gives us some idea of how all these things work. So notice, mu s and mu k can change very, very greatly. I mean, the difference between cast iron, between when it's moving and when it's static, is vast, huge change. That's almost a tenth of what it started off as. Yet rubber on concrete isn't that much of a change. It's definitely still a change, but it's not giant. Ice on ice, once again, pretty large change there. Teflon on Teflon, Teflon starts off with a very low friction coefficient, but it stays the same whether it's moving or whether it's still. Teflon's the stuff that they make non-stick, that goes onto non-stick frying pans, and Teflon's actually a brand name, and there's a specific chemical name, but no one ever recognizes that chemical name unless they've learned it before in chemistry. All right, so this gives us some idea of what it is. We start to see that mu static is almost always larger than mu kinetic. Sometimes they're equal, and like I said before, there are a few freaky cases where mu kinetic is going to be larger, but that's really something that's more for complicated theoretical experimental stuff, not something we'll see in high school physics. So for our purposes, mu static always greater than or equal to mu kinetic. It really can vary what it is. We see, massive changes all the way from 1.1 to 0.04. You can have even higher than 1.1. The grip of a rock climbing shoes on rock is going to be even larger than 1.1. The mu kinetic can get very, very small. Mu static can get very, very small. It really depends on the situation. You have to get it in either the problem statement or that. For the most part, we'll see numbers between like 0.2 and 1 at the very highest, but if it's really slippery objects, we'll see even lower. It has to do with what we're getting in the problem and the specific materials we're working with in our case. All right, one special thing to talk about is wheels. How do wheels work? So you might think at first that wheels are going to have kinetic friction between the road and themselves because they're moving. Not actually true. So one special thing to notice is that when a wheel rolls along a surface, it's going to use its static friction, not the kinetic. Now, why is that? So when the wheel is rolling, at the moment of contact, consider this sort of like flash forward thing. We've got some point here, and then that point's here, and then that point's here, right? So at the moment of contact, when it's right here, when it's on the ground, it's actually still because it gets laid down and then it gets picked back up. It doesn't move relative to the ground until it's off of the ground. If we've got this perfect circle wheel rolling, the wheel isn't actually going to wind up having any friction on the ground. In reality, the contact patch does move slightly, but we're talking extremely small rolling resistance frictions here, like 0.001, that sort of scale of like very, very small. So for our purposes, we can pretend that there's no friction from a rolling wheel if it's able to stick to the ground, if you aren't in a slide. So static friction is what you use for a wheel. So notice this doesn't mean that a car is being slowed by friction through the wheel. Static friction can be very large. We're just seeing numbers up to like 1.0 for a wheel on concrete in dry conditions. But that doesn't mean that the car is taking all that out. In fact, because it's being put down and then it's moving off, it never moves. It's never trying to be moved around. When it's on ground, it's like it's practically still. It's perfectly still from the point of view of the tire at that moment. So that piece, that dot, doesn't start to move away until it's off of the ground. Once it's off the ground, it can move around because it's not going to have any friction. So the only thing that would create friction is that tiny contact patch, but because that tiny contact patch is picked up before it moves relative to the earth, relative to the road, it's not going to give us any friction force on our car. So on the contrary, the fact that it's in static friction is what's going to allow the car to move smoothly and experience practically no friction. By having good bearings and good oil, by being able to have a good wheel system, you're going to be able to have a almost frictionless motion, and you'll be able to have all of the motion of the car translated easily as if it's running frictionlessly. At least that's what we'd hope. In reality, there's going to be some slight friction because nothing's perfect, but it's going to be pretty darn good. It's going to be way better than if we just had a metal body on the ground that we were shoving along. So the wheel will experience effectively no friction while it rolls along the ground in a straight line. When the car turns and tries to change its velocity, either by accelerating, so it's suddenly going to have those contact patches spinning up because they're going to be moving faster than they were before, and this is a little complicated to think about, but the acceleration, the force, it's friction forces that allow the car to get that traction, which is why you see stock cars, racing cars have really, really big, flat, large wheels. Is because they want a really, really big contact patch so they can get lots of force into the earth. Whereas cars that are like trying for efficiency tend to have much thinner wheels. They're going to have less contact patch. If you want to be able to get a car that gets better fuel efficiency, you pump up the wheels a little bit heavier because that will make them firmer, tighter, so they'll have a less contact patch on the ground, which means they'll have a little bit less friction. Remember, these are very small numbers, but if you're driving 100 miles, it can start to have an effect. Or if you were to turn, that's when friction is going to come into play because, and we're going to have to diagram this in my hands because it's too hard to actually do as pictures. Normally you'd have the wheel running like this, but then if we want to turn, the wheel's going to turn like this, but the motion of the car is going to be going like this. So normally your wheels are going like this and we have effectively no friction. If instead we turn, the car has two choices. It can't actually make a choice, but if it were to keep going in this path, then all of a sudden friction, we'd be breaking its contact patches with the earth because that's not the direction the wheel wants to roll in. Instead, it's going to go this way. So if the car were to keep going this way, it would break friction. Friction would fight it. So instead, it goes this way, which means that friction is going to wind up actually pulling this way. This is a little bit complicated to think about, but the force of the wheels, friction is the only thing that connects the car to the earth. The car and the road are connected through the friction of the tires. So when you go into a turn, the thing that pulls you into the turn is going to be the friction of the wheels on the ground, and it's going to be mu static. Now, this is a lot of explanation for something that doesn't seem to make sense, but if you want to be able to understand how a car rounds a corner, like we will in the next section when we talk about uniform circular motion and force, we're going to actually have to be able to understand this. And so this stuff actually matters, and it's a little complicated to think about at first, but it'll make sense. If something's going to be rolling, it effectively has static friction, it effectively has no friction because it's going to be putting down its contact patch and then lifting it up. But if it wants to have an acceleration, that contact patch suddenly has to move relative to the ground, otherwise the rotation movement of the wheel is going to change the speed that the wheel is moving along, so it's going to require friction to be the interaction, the interplay between those two things. All right, let's finally get to talking about the examples for normal basic friction. So we've got a block of mass 10 kilograms resting on a flat surface and has a horizontal force acting on it. It just barely begins to move. It unsticks at the force F equals 60 newtons. So what is mu S? All right, so first let's do a quick free body diagram. What forces are operating on this? Well, there's mg pulling down. So flat surface, there's nothing else pushing down on it. It's a horizontal force. So we know that Fn is going to be equal to mg. It's going to cancel one another out. So now we're going to work towards figuring out what our friction is. And we know that friction is going to pull this way. So if mu S is what we're dealing with right now, if we're dealing with static friction, the moment of unsticking, that razor's edge between staying still and just beginning to move, is going to be the maximum static friction. It's going to be the maximum static friction is going to all of a sudden equal the force. Not all of a sudden, it's going to be continual, but the force is going to be equal to the maximum static friction for it to unstick at 60 newtons. So what's the maximum static friction? That's mu S times Fn. What's Fn? Well, that's mg. So we've got mu S times mg. What's the F? Well, F is equal to 60 newtons. So For it to just unstick, we know that that maximum static friction had to just be beaten, just barely, on that razor's edge where they've just equaled. As soon as you surpass it, you flip into motion, you switch over to kinetic. So that precise moment of when they equal is the moment of unsticking. So now we just plug in our numbers. So mu s equals 60 over mg. Well, we know what the object weighs. We know what gravity is. We've got 60, 10 times 9.8. We punch this into a calculator, and we figure out that mu s is equal to 0.61. So for this case, between this block and this surface, we've got a mu statics equal to 0.61. All right, so once it starts to move, it still has that force of 60 newtons on it, and now it has an acceleration of 1 meter per second per second. So we know that the sum of the forces is equal to the mass times the acceleration, right? We know what the acceleration is. We know what the forces operating on it are. We've got the force up here, which is equal to 60 newtons, minus the force of friction, kinetic, right? So mu k times mg. So friction force. So here, and we know that that's the mass times the acceleration. What's the mass? 10 times the acceleration. What's the acceleration? 1. So we've got 60 minus 10 equals mu k times mg. 50 divided by mg equals mu k. We punch this into our calculator, and we get that mu k is equal to, we plug in our numbers for m and g, and we're able to get that it's 0.71. There's our answer for what mu kinetic is. All right, next example. All right, so for this example, we've got a block is resting on a surface that can be tilted. So we've got some tilt theta on our surface. The coefficient of friction between the block and the surface is mu static equals 0.35. What angle theta will the block barely begin to slide? What is that instantaneous, that razor's edge, that breakover point between staying still relative to the incline and suddenly starting to move along the incline? Notice, for this problem, we don't have the mass of the block, but it turns out we're actually not going to need it. So let's start looking at this. Where a block, it's going to weigh some m, so mg is the pull of gravity on it. How much of this is going to be perpendicular? Well, the perpendicular force is going to be is going to vary depending on what our theta is. How much is the parallel force? Well, that's also going to depend on theta. What's theta? Well, theta is going to wind up being here. And we can figure this out by referring to that old lecture that I had on Newton's second law in multiple dimensions. But we can also see that in the extreme case where this was 90 degrees, then we'd have that this was going to be sine of 90 degrees. So we'd have all parallel. And in the case where it's 0 degrees, the other extreme case, we'd have cosine of 0 is equal to 1, so it'd be all perpendicular. So we see that the theta has to go here, but we can also figure that out through other geometrical means and just getting used to it, used to how this works. But if it doesn't make sense, this is definitely a good thing to go refer to, because this can be a real confusion down the road. And there's lots of problems that involve incline, so it's really important to have a good understanding of how this works. All right, so this is mg. Then we have that the perpendicular force of gravity is going to be equal to mg times cosine theta. So how much is the normal force? Well, that's going to keep it from bursting through the incline. So we have that Fn equals Fg perpendicular, which is equal to mg times cosine theta. Great. What's the parallel force? Well, the parallel force is just going to be sine theta times mg. Great. So we were able to do that all because we had a right triangle, because those two things are perpendicular. And so we just use basic trig. So at this point, what are the forces acting on it? Well, at this point, we've got the parallel force going this way. Sine theta times mg is going to be equal to gravity parallel. All right. What one other thing is we're operating on it? Friction. Friction is going to be pulling backwards. We're going to be using static friction because the block starts off at rest. So what is the moment of flip is going to be when that maximum static friction is just equal to FG parallel. When those two things just equal, that's the razor's edge, that's the moment of flipping. So what's maximum static friction? That's mu s times Fn, using a capital, is equal to Fg parallel, which is sine theta times mg. What's Fn? Mu s times mg times cosine theta equals sine theta times mg. Hey, look, we've got mg on both sides. This is why we don't need to know the mass. So we cancel out that on both sides. And now we've got mu s times cosine theta equals sine theta. Well, we can collapse that into one trig function by dividing by cosine theta. And since sine theta over cosine theta equals tan theta, we've got mu s equals tan theta. So now we've done this in general. If we want to know what the angle is, we plug in our numbers. We've got 0.35 equals tan theta. So we go and we take the arctan, the inverse tan, on that 0.35. That'll give us what our angle is. We're doing this in degrees, and that will come out to be, we punch it into our calculator, we look at it in a table, and that'll get us 19.3 degrees is equal to theta. And that tells us what the specific angle is. But it also tells us, in general, if we want to do this for anything, that's a really easy way to figure out what mu static is for any pair of objects. For any material on some surface, you just have a careful way to be able to measure the angle, and you just keep very, very slowly tilting it up until it just begins to move. Really easy way to experimentally derive what mu static is going to be. All right, example 3. We have a block against a wall and it's sliding down. If the coefficient of friction between the block and the wall is mu k equals 0.2, how hard do we have to push against the block to cancel out gravity to give it a constant velocity? So if we push in with some force here, what's the normal force going to equal? It's just going to push back with the exact same amount. So Fn equals whatever force we put in terms of magnitude. So what's going to be operating on this in addition? We've got gravity pulling down by mg, and we've got friction pulling up by some amount that's going to be connected to its mu and the force of friction. By its mu and the normal force, that's what will determine the friction. So are we moving or are we not moving? In this case, we started off knowing that the block is sliding down. So that means we'll be using mu k, mu kinetic. So what's the force of friction? Friction's equal to mu k times Fn. So that means that in our case, it's going to be 0.2 times Fn. What's Fn? It's however hard we're pushing against it. It doesn't burst through the wall, so the amount that we push in is the amount that the wall has to resist. So we've got that mu k times F, force we're pushing, is what it is for this problem. If we want those two things to cancel out, then we want an acceleration equal to 0. So that means that the sum of the forces is going to have to be equal to 0 because mass times acceleration, so that cancels out to giving us 0. That's the way we're doing it right now, because we know that we're in equilibrium because there's no acceleration. It is going to have a velocity. It is sliding down, why we're using mu kinetic, but we know that there's going to be no acceleration. So the net of the forces, what forces are acting on it? Gravity is acting on it. Friction's acting on it. We also have, in the horizontal direction, the force that we're pushing and the normal force, but they cancel each other out. We don't have to worry about that because it's just, staying parallel to that wall. So all we have to worry about is the things that can have an effect, which in this case are gravity and friction. So let's say that up is positive. So we've got that the friction force minus mg equals 0. So what's the friction force? It's mu k times F minus mg equals 0. So we've got mu k equals, mu k times F equals mg. So F equals mg over 0.2. So in this case, we didn't do it with we did a general version, we did it with any block. So in this case, we've got that the force that we have to push is going to be 0.2 when it's dividing is the same as 5 multiplying. So 5 times the weight of the object if we have a kinetic friction of 0.2. And this could be used to solve generally the way we did this. So we've got the friction is the amount of force we have to push to keep it at a constant velocity or keep it still if it started off still and we're using mu static is going to be dependent on the coefficient of friction. So in this case, it's 5 times the force of gravity. All right, last example. This one will definitely require some thinking. So we'll start off thinking about the problem and then actually approaching it, which is a great way to approach your problems in general. Think about it, then approach it, then actually do the math. So we've got two blocks of masses m1 equals 2 kilograms and m2 equals 1 kilogram. They're sitting atop each other, and they have a coefficient of friction, mu static, equals 0.7 between them. The bottom block is resting on a horizontal, frictionless surface. What's the minimum force to keep the top block from slipping? All right, so first of all, if they're moving at the same rate, what does that mean? Well, then that means that we've got some a1 acceleration, and we've got some a2 acceleration, right? And they're both going to be moving in the direction of force. So these are our accelerations are going to be going this way. But what about the fact that if they had different accelerations? Well, what would it mean if they had different accelerations? If they had different accelerations, then one of them's either going to be sliding off of the other or, sliding behind the other. There's going to be a difference in their relative velocities, which means that they have to have, they can't be staying together anymore. It has to be slipping by the definition of slipping. So that means, just to begin with, we know that the acceleration of the first block has to equal the acceleration of the second block. So we can just call them in general A. So the accelerations are equal between the two. All right, what else do we know about this? What keeps block 2 on top of block 1? Well, there's no forces that we're putting in externally. There's nothing on it. The only force that's keeping it there is the force of friction. M1 is moving this way. So that means that for them to stay attached, static friction wants them to stay in place. M2's friction is going to pull this way. So we've got friction moving this way. And, I just drew these in. These are the same thing. So friction is going to be pulling block 2 over. What about block 1 will result in force? So M1 is going to be reduced by that same friction. These will be equal. Equal in terms of magnitude, not direction. So M2 is going to be accelerated by friction. M1 is going to be decelerated, or at least lose some of its force to friction. All right, so that gives us an idea of what we're actually doing here. We've got these two blocks. They're pulled along. Only the bottom one is being pulled along. And the way that it's able to communicate to the top one, the way that it's able to cause it to move, is by using friction. The bottom one and the top one, they only communicate through friction, so friction has to be the thing here. If we're able to put so much force, and this makes sense, I'm sure you've seen it, if you've got two books on top of one another and you yank the bottom book really hard, the top book will just fall down. Whereas if you yank the bottom book slowly, you don't yank, you pull gently, they'll both slide along easily together. This is going to be connected to the coefficients of friction and the masses of the books. All right. So what's going to be that minimum force to keep that top block in place? Well, I'm sorry, what is the minimum force to cause it to slip? What is the maximum force to keep it in place? They'll be the same thing, as it's that razor's edge once again between slipping and not slipping. But now we've got the understanding to actually approach this problem. All right, so final thing, now we can actually do the math. So let's start looking at the two free body diagrams. So in this case, we've got some force, right? What else is operating on it? Well, we've got friction from the top. What about its own friction? Does it have its own friction from the ground? No, remember we said that it's on a frictionless surface. So in this case, there's only one friction. There's just the friction between the blocks, right? Between the blocks is the only friction. Okay, so what is mu s? We know mu s. What's normal force? Well, how hard does M2 push in? M2 is going to push in with M2 times G, so Fn equals m2 times g because it doesn't burst through the box. It doesn't move through it. It stays on top of it. If we just let it alone, it would sit there. So that means that the normal force has to equal m2 times g. All right, so with this in mind, we can start coming up with our formulas. So net forces, we know that F will make this the positive direction. We know that F minus friction equals the mass m1 times the acceleration, right? And we could, we'll make these all vectors, but it doesn't really have to be because we understand the directions because they've been dealt with. Technically this one can't because it's a minus here and we have positive, but anyway. So F minus friction equals m1 times A. What is the forces on m2? Well, just friction equals m2 times A. All right, well, with that in mind, we can start to figure out what is F going to have to be equal to. So, well, F, we sub this in, we get F minus m2 times acceleration equals m1 times acceleration. So we've got that the force equals m1 plus m2 quantity times the acceleration, right? So that's how much force is necessary to give an acceleration to this, because it has to move both of the objects. It has to move the whole system. All right, we can sub that back in though, and we can now figure out what is friction. So F over m1 plus m2 equals the acceleration. We plug that back in to this formula right here, and we get that the friction is equal to m2 times F over m1 plus m2, getting a little cramped there. So we've got that friction is equal to the force m2 times the force over m1 plus m2. So now we could sub these things in and we could figure out what are the actual numbers. What also is friction? So in this case, we've got that friction is equal to m2 was 1 kilogram, so F over 1 plus 2, 3. So friction's equal to F over 3, because that's the amount that it has to get. It's the share that the top block has to get because it has 1/3 of the total mass of the system, so it has to get its equal share for its mass to be able to move at the same acceleration. So the friction has to be equal to F over 3 for the acceleration to be the same between both objects. So what's the maximum amount of friction? Remember that it's going to have maximum friction and maximum static friction, I should say, because we're static here. Maximum static friction is going to be the maximum velocity without slipping. So once again, it's that razor's edge. So the velocity, the minimum velocity for slipping is going to be that flip over point where the maximum velocity without slipping is going to be the same thing as the minimum velocity of slipping. If we just go over just a hair, just 0.000001, just infinitesimally smaller amount over, we're going to suddenly start to slip. So the maximum static friction is equal to the maximum velocity that we can move at. The maximum force, maximum velocity, maximum acceleration. Actually, I shouldn't have said velocity, maximum acceleration. My apologies. It can, of course, have any velocity. It can be whizzing along through space at, 1,000,000 miles per hour. It doesn't matter because from its point of view, it's not experiencing any force. So it's about the maximum acceleration. So maximum force. Okay. So with all that in mind, we're going to have that it will slip at the moment when F over 3 equals max static friction. What's max static friction? Mu s times m2g, or normal force. So if we want to figure out what that is, F equals 3 times mu s times m2g. We just plug in a bunch of numbers now. We use our calculator at this point. 3 times, what was mu static? It was 0.7. What was the mass of the top object? It was 1. What's gravity? 9.8. So that gives us that the Newton force When we use as a calculator on this, we come up with the number. It's 20.58 newtons. That's how much it is to finally get the thing to just start slipping. If we just barely exceed 20.58, that's the razor's edge, the slightest bit of difference off of 20.58, and it will just start to slip because we'll have just exceeded this maximum static force. All right, great. Hope friction made sense. Make sure, if you've got difficulty with understanding how an incline works, definitely refer to Newton's second law in multiple dimensions. It'll help you get an understanding of how to deal with parallel and perpendicular forces. That's where you want to get that because it's important if you're going to start working with friction heavily. All right, hope you enjoyed it. I'll see you later. Thanks.